Okay, so good morning. This is our 10th Classical Mechanics 1 meeting. Today is Thursday, the 1st of September, 2022. So welcome back after yesterday's holiday. Are there any questions that you would like to ask before we get started? Okay, if not, you're welcome to ask later. So last time we had introduced some important foundational concepts concerning Newtonian mechanics, concerning principally the approximation that light travels at infinite speed, and that one had an absolute notion of simultaneity that all observers could agree upon. So there is a sort of an absolute time for everybody. We can all synchronize our clocks, and this was the assumption made by Newton. Yeah, so that you are aware, Newton's work is from the late 1600s. His book, the Principia, was published in 1687. Mathematical Principles of Natural Philosophy, because it was in Latin. It was, of course, the culmination of the work of several people, including Newton himself. He had earlier attempts at the laws of mechanics. In fact, even an earlier book where they were slightly differently presented. Yeah. Okay. So, but that was only the starting point of kind of mathematical presentation of the laws of physics and their consequences. It was, of course, founded on earlier work of especially Galileo, who was in many ways his predecessor. Among other things, I think Galileo died in the year that Newton was born, 1642. Yeah, but there were many people who came after that as well. In the 1700s, principally the Bernoulli family, Johann and Daniel Bernoulli, and I think Daniel's student was Leonhard Euler. You may have heard of Euler. So all these people contributed tremendously to the development of mechanics. Of course, in the context of terrestrial as well as celestial phenomena. By terrestrial, I mean things that we see on the Earth, moving bodies, falling balls, and projectiles, and so on, as well as celestial phenomena, such as the motion of planets, the moon, and so on. Yeah. So, but of course, these things go back much before Galileo. It was a development over several hundred years, slowly to identify concepts like instantaneous change of position. That is a relevant concept, concept of velocity. These things took a long time to develop. Okay, so I hope our friends are all here. So while I'm at this, Yeah, so Newton in many ways developed calculus for the purpose of understanding mechanics, especially celestial mechanics. And I mean, the physics required certain concepts to be developed, and it forced people to do those things. Of course, at that time, calculus did not exist. The more developed subject was geometry. So most of his work on mechanics was actually presented in a geometric framework, including in the Principia, so that it would be more easily understood by his contemporaries. And of course, many of the tools of calculus did not exist at that time. Some of them were developed by Leibniz. So where was Newton from? Which country?
England.
Indeed, yeah. And he spent a significant part of his working life in a particular university, which is
Oxford.
Well, okay. Well, you could be 50% right, but the one he actually spent most of his time was not at Oxford. It's the other one.
Cambridge.
Indeed, Cambridge. Yeah, and he was a Lucretian professor of mathematics over there. Yeah, Leibniz was from which country?
France, I guess.
Your guess is a neighbor.
Germany.
Germany, indeed. Yeah, the Kaustub. Yeah, Germany. Yeah, and I guess I mentioned the Bernoullis. Bernoullis are again a very illustrious family from. Okay, you must tell me from which country.
This one, I guess, was France.
Okay, if you keep saying France, you will eventually be right. But
I guess they were from Italy.
No, France, Italy are both neighbors. So now you have one more chance.
He was Swiss.
Yeah, they were both Swiss. So they're from Switzerland. I think it would be fair to say it's the maybe the German-speaking part of Switzerland. But please check that. I'm not 100% sure. That is my suspicion. Yeah. And Euler, from where was he? Which country? I kind of gave it away earlier.
Russia, Euler, Russia.
Okay, so somebody said Russia. Who was that?
No. He went to
I guess
Russia.
it was Switzerland or
sorry,
Italy, because you mentioned he was a student of
Euler.
Bernoulli.
Indeed.
Euler was born in Basel.
Basel is in Switzerland. Yeah, Basel is in Switzerland, and so yes.
Later he went to Russia.
Yeah, indeed. Yeah, so he did. I mean, he worked in Russia for a significant portion of his career. Euler worked in Russia. In fact, in St. Petersburg, the northwestern coast. Yeah, he was there. The patronage of the royals, but he also worked in Germany for a long time, Euler. So he went between these two places. A truly remarkable scientist. So all these people did a lot of work in celestial mechanics, and that was one of the main source of ideas. Yeah, but there were others. Since you are very keen on people from France, the next, yeah, I mean, along with Euler, there was D'Alembert, and he indeed was from France. Clairaut, we have already mentioned in the context of Clairaut's theorem on equality of mixed partial derivatives. So Clairaut, Alexis Clairaut is also from France. So. And then there were other giants, Lagrange. And Lagrange is from where?
Sir, I'd guess France again because his name sounds French.
Yes, you're quite right. He is from France, but in this case, the Italians will also claim ownership, because I think he was born in Italy or the border, something like that. But he spent most of his life in France. He is considered French for most part. Yeah. and then Laplace, Pierre Simon Laplace, also French. So these are all very illustrious figures in the history of mechanics. So Newton's approach was very geometric and very clever techniques. In fact, I'm not sure that most of us can reproduce that level of geometric thinking now. We are more accustomed to doing things to analysis through calculus, and there is some advantage to that. And that really came at the time of the Bernoullis and Euler. And it was in many ways a good addition to the toolkit. On the other hand, Laplace, So anyway, when we come to those things, we will tell more about such things. Okay, but let me return to where we were last time, which was on Tuesday. Of course, we had a little tutorial yesterday. We discussed some of the problems from problem set 3, and I am glad that some of you were present. Okay, so last time we spoke about but I wanted to mention one thing. I mean, it's actually to do with some of the questions we have received. So the way physical science works is that we observe things or we measure things, and then we try to deduce some patterns in those observations, and then see whether we can model them using mathematical concepts or equations or constructions, structures. So which mathematical structure is relevant to a particular physical phenomenon is not a priori clear. It is only through trial and error that one, or some inspiration, guesswork. So it's through looking at specific, so there's two parts. One is direct experimental observations. And then once you're somewhat familiar with the phenomena, you want to build simple models for those things, because the actual physical phenomena usually involve too many complications. Like there is usually friction and gravity, and there is also some force from some piston pushing something. So that requires some insight of which forces are important, which are less important, which frame in which to view it. All these things are enormous amount of physical insight is needed to distill the key properties of a system, and then find appropriate mathematical models to model those key features. The relevant mathematics typically doesn't exist. In some cases it may in some form, but usually it doesn't exist, and we need to invent it. And that is precisely what Newton did. That doesn't mean calculus did not exist in some form. The rudimentary form of calculus already existed. In fact, that goes back much earlier, especially to Kerala School of Mathematics and Astronomy. Many concepts of power series, convergence, and so on had been already developed. But the infinitesimal calculus really was developed by Newton and his contemporaries. But even that was in today's language very not in the language we would currently use. That took a long time. I mean, the things like limits and epsilon delta definitions, they came nearly 150 to 200 years later in the work of Weierstrass and Cauchy, who are the ones who put calculus on somewhat different or in some ways more rigorous footing. So we need to understand that the development of mathematics and mathematical physics is a complicated process. It is in books, sometimes we present things as, in mathematical textbooks, things may be presented as in the sequence definition, proposition, theorem, lemma, proof. This could not be farther away from the actual development of physics or mathematics. It certainly doesn't go this way. We start with examples, we start with conjectures, we start with guesses, we start with talking to our friends, and we start with looking at nature. The definition is the last point in the development of a subject in this sense. To find the correct definition of a concept requires 100 examples to know what is right and what is not. So I want to convey to you, we will talk about this as we go, but the correct definition of a physical concept or the correct level of mathematical precision that you need is definitely not a priori clear. And to make a choice of that at an early stage of the development of the physical theory will be a big mistake, because putting some constraint like that, like I want to study only functions which are 3/4 differentiable, will seriously rule out many physical phenomena. Or so one needs to play a back and forth game, and in many ways the definition comes after after the theorem has been understood. You need to know under what conditions you know the phenomenon already, because nature is telling you, and you need to figure out under what hypotheses those theorems will be true. So that is the way it really works. And I'm not saying this only about physics. This is true about the best mathematics as well. It is based on guesswork and conjectures. And to give a correct definition of a manifold, current definition, it took many years, several decades. Came only in the middle of the 20th century, work a while and so on. So whereas we had hundreds of examples of manifolds in excruciating detail long before any definition was available. So this is the way it works. But that is not to say we don't seek definitions. We do seek definitions. We do seek precision. But it needs to go hand in hand with what the objective is. Okay, with those remarks, let me continue with what we were saying. So we were speaking about degrees of freedom of a system. So 2-point masses moving in 3-dimensional space have 6 degrees of freedom, all right? And that's because we need the 6 Cartesian coordinates, namely x, y, z of the first particle. Well, this should have been y1, x1, y1, z1 of the first particle, and x2, y2, z2 of the second particle, to specify the locations of the 2 particles. All right. So, for example, if we study the Sun-Earth system regarded as point masses for now, okay, so to some approximation, the Sun and Earth can be treated as point masses, then this is a system with 6 degrees of freedom. Okay, which would mean that to predict the motion of the Sun and Earth, you would need to specify 6 initial coordinates. No, I take that back. We would, to predict the motion, you need more. But at the very least, to locate the system initially, you need to specify 6 real numbers, just to know where the Sun is and where the Earth is. It turns out even that is not sufficient. So we'll come to that. So I must emphasize that in discussing degrees of freedom, we do not restrict to a particular orbit of the Earth around the Sun. Yeah, I mean, you may know that the Earth goes in an elliptical orbit around the Sun or a circular orbit, but that is not relevant to identifying the number of degrees of freedom. So we simply ask how many coordinates are needed to specify all possible locations of the Sun and the Earth at any fixed instant of time, without reference to the nature of the force between the two, nor the nature of a particular orbit that one may observe. Okay, so it's a question of all possible locations of the Sun-Earth system at one instant of time. Okay, let me take a slightly more sophisticated example, namely a rigid body. But any question so far about degrees of freedom? All right. Now, let's take a rigid body. By rigid body, I mean one that is not deformable. So this pen is a rigid body, for instance, or a stone for that matter. A rock. These are all rigid bodies. Yeah, but it's extended. It's not a point particle. It's extended. So it's made up of several particles, if you wish. But the distances between the particles in the stone are all fixed. Yeah, they are not changing with time as the stone moves. Now, I claim that a rigid body like a stone has 6 degrees of freedom. Okay, so let us try to enumerate what these are. We will do it in a manner that is convenient for us. So for convenience, we may enumerate them as follows. Okay, I claim there are 3 translational degrees of freedom, which are just like the 3 degrees of freedom for a point particle, right? You need to say where it is. So you need to give the x, y, z coordinates of the particle's location. Same way here, we need 3, and we call those 3 translational degrees of freedom because you can move the particle from here to there. So it has to do with translation. So that's why it's called translational degrees of freedom. So we need 3 of them to fix the location of a marked point in the rigid body. Okay, so we take the rigid body, maybe this pen, we mark a point on it, maybe the pen tip of the pen cap, and we move it to the desired location, the pen cap alone. So in doing that, I need to specify 3 coordinates. I mean, how far from my nose horizontally, how much down, and how much to the right or to the left. Okay, so I need 3 degrees of freedom to locate a marked point in the body. You choose any marked point, whichever one you like. In addition to that, having located the pen tip, I have still a lot of freedom in locating the rest of the pen, right? In fact, I can rotate it in any which way. It's more than that. I mean, a pen is somewhat of a bad example. Maybe I need somewhat bigger object. Yeah, this bottle, for instance. Suppose I have located the cap of the bottle somewhere, then there is still yet more degrees of freedom. And these are 3 in number. There are 3 rotational degrees of freedom, which are needed to orient the body holding the marked point fixed. Okay, so I hold the mark point fixed, and the mark point may be some point on the tip of the cap of my bottle. And then I can do many things. I can rotate the body, all of which are done holding that mark point fixed. I can even spin the body about that mark point, about some axis passing through that mark point. So I claim that there are 3 rotational degrees of freedom to orient the body holding the mark point fixed. I hope you are able to imagine this. Would you like to give any comments on that or questions about this before I elaborate?
What's the mark point?
A mark point, by that I mean a point in the rigid body, a point in the stone, which I choose as some kind of a reference point. So I take a little bit of paint and I go and mark it with that paint. Of course, if it is on the surface, if it is deep inside, then I can't put paint. Yeah, but that is what we mean by a marked point. It is a reference point. I could call it a reference point. The word mark point is used commonly in topology and so on. But anyway, it is just a reference point. And the idea is that you will bring the reference point to its desired resting place and then orient the rest of the body as desired to reach the desired orientation. Now, the desired orientation in general will involve a rotation about 3 axes. You could think of 3 cardinal directions: the x-axis, y-axis, z-axis with respect to this room, the walls of this room. And you could make rotations about these 3 axes to bring the body to its desired orientation. I could even say it differently. Having brought the point on the cap of my bottle to its desired location, I can still I can define some axis through it, through the body, maybe the axis of symmetry of this bottle. I can make rotations about that, right? So those are also allowed. I mean, if I rotate the body, then it changes. And then I could also move it on a sphere centered at that marked point. Okay, so and that gives you 2 more degrees of freedom. You have points on a sphere, all of which are available. So you got 2 more degrees of freedom in addition to the spinning motion. So that's how I have 3 rotational degrees of freedom. Is that plausible? Okay, we will see more examples as we go on. Now let's look at another. See, we started with a point particle, then we went to 2 point particles like the sun and the earth. Then we went to a rigid body. Now we can go to the other extreme, like a fluid, like the air in this room. There are a lot of air molecules in this room. In fact, there are roughly 10 to the power of 24 air molecules in this room. There is a name for the number which estimates the number of molecules in a mole of a substance. So what is that number called?
Avogadro number.
Yeah, indeed. So Avogadro's number is an estimate of the number of molecules. Yeah, so we can talk about that later, but my key aim here is to tell you how many degrees of freedom the air in this room has. So we would, okay, again, it's a question of how you model the molecules. For simplicity, let us suppose the molecules are modeled as point particles. Yeah, for some purposes, this is an excellent assumption. Yeah, and then we have to enumerate the degrees of freedom. Certainly, it's a very large number of degrees of freedom. We can take them to be the 3 times n. So suppose there are n molecules, then for each molecule, which is regarded as a point particle, you have 3 degrees of freedom, 3 translational degrees of freedom, which determines its location. So 3 times n. Cartesian coordinates would be needed to specify the instantaneous locations of all the n molecules, which are treated as point masses. Okay, so a system of n particles has 3 n degrees.
So what about a rotating fluid?
A rotating fluid? Okay, actually, the manner of motion of the fluid does not affect the number of degrees of freedom. Okay, the manner of motion of fluid doesn't affect the degrees of freedom. The degrees of freedom is a very primitive concept. It comes before we talk about how the thing is moving. So it's a good question you have raised, Ankon. The number of degrees of freedom in a rotating fluid is the same as the number of degrees of freedom in any other type of fluid. It is simply 3 times the number of molecules present. Even if the fluid is rotating or the bucket is rotating, whatever, you still need to specify 3 n coordinates, say Cartesian coordinates, to locate all the molecules at one instant of time. What happens at the next instant of time is a matter concerning the dynamics of that system. It may rotate in some uniform way, it may be moving rightward, maybe moving in a random fashion. That is all separate questions. Those are all separate questions.
Sir, are point particles said to not have orientation?
Correct. Yeah, we are. The concept of a point particle is a extremely useful concept in physics. Yeah, and it is a object which we postulate to not have any rotational degrees of freedom. I mean, it is simply a point. So there is no meaning to say it is oriented towards Jupiter or anything. It is simply a point. So point particles do not have any rotational degrees of freedom or orientational degrees of freedom, unlike a stone. A stone really can be oriented as we wish because it's an extended object, whereas a point particle is not extended. Is that okay? Okay, I could not hear. All right. Now we introduce a technical term. We call it an instantaneous configuration of a system. Yeah, what do we mean by that? Well, through an example, let me introduce this. An instantaneous configuration of a system of 2 point particles is any possible location of the 2 particles at one instant of time. Okay, so an instantaneous configuration of a system is a possible location of all the constituents of the system. So you locate all the constituents of the system where you wish them to be or where they are. that would be designated as an instantaneous configuration. With the time, that configuration is likely to change if the particles or bodies move around. So we will use this term again and again, and you will get used to it. So instantaneous configuration is simply an instantaneous location that is adequate for us right now. Okay, any comments on this so far? Okay, if not, let us now proceed to what I would like to call the zeroth law of classical mechanics. And let me try to state what I mean by that. Yeah, so now we are beginning to look at systems or particles and try to deduce what kind of the character of the physical law that may govern their behavior. Okay, so we are going to summarize those things. So the first such statement is the following: the path followed by a particle in time is called its trajectory. Okay, so that is simply a name. A path followed by a particle is called a trajectory. It is a curve parameterized by time and directed towards increasing time. Okay, so it's a directed curve in the set of possible locations of the system. Okay, so it's a curve in the configuration space, technically speaking. But if it's just one particle is moving in this room, it will trace out a curve, and that curve is called the trajectory. Now, we would like to say that the zeroth law of mechanics can be regarded as saying that the trajectory r of t of a particle is a twice differentiable function of time. Okay, so this is a very significant deduction from observation of motion of objects. I would like to emphasize. So again, the statement is that the trajectory of a particle is a twice differentiable function of time. Right. So I want to emphasize this is a law of nature. This is not a self-evident fact. It is not an assumption. Yeah, it is a law of nature. So let me say that again. This is not an assumption, but rather an assertion. It is an assertion about natural phenomena deduced by observing the motion of terrestrial and celestial bodies, such as cricket balls and planets and so on. This assertion applies to the motion of planets, pendulum bobs, cricket balls, etc. So this is a law of nature that applies to certain objects. Okay. Yeah, when I say a law of nature, we usually mean it is something that we deduce from observation. It has a domain of validity that it applies to certain phenomena or certain objects, usually a limited domain of applicability, and it is not a self-evident fact. So laws of nature are not self-evident. They are not some play with words or some I am, therefore I am. It's not that kind of a statement. This is a deduction from nature. Okay, and a law is usually interesting, provided it also fails. Right? So there should be places where it fails. Yeah, usually that is the case. So this law that I just stated has a limited domain of applicability. It fails in many physical phenomena. For instance, it fails for the Brownian motion, which you may have heard of. What is Brownian motion? It is the movement of pollen grains in water, and through a microscope, it is possible to see that these Brownian particles or the pollen grains are observed to follow very jagged paths, very jagged paths, which is not fruitful to approximate those paths as a twice differentiable functions of time. Okay, so there are motion of particles such as Brownian particles for which treating them their trajectories as twice differential functions of time is a very bad strategy. Yeah, so so I want to emphasize that this law has a definite domain of applicability. This law also fails for electrons in an atom, which it was found, it is very hard to define what you would mean by a trajectory of an electron in an atom. The concept itself is somewhat fishy. It cannot be made physically precise, and a somewhat different framework is needed, which requires a quantum mechanical treatment. Okay, so I have just now mentioned two very, very big examples, namely Brownian motion and quantum motion of electrons in atoms, which do not satisfy what I call the zeroth law of classical mechanics. Okay, so we should know the domain of applicability also of our laws. Any question about this statement?
So one question is that why only twice differentiable? Why not thrice or 4 times? Right?
Yeah, the answer lies with nature. We observe nature. As I said, this is not a mental deduction. It is an observation from nature. It could very well have been thrice differentiable functions of time, or once differentiable functions of time, or half differentiable functions. All these possibilities exist. We have to go out and experiment and find out what is the minimal requirement that nature is providing to us. It is true that in many cases, the path of a particle is actually 5 times differentiable, maybe even infinitely differentiable, if you could do all those differentiations using experimental data. But that is too much. The minimal requirement is only twice differentiable, and once differentiability somehow is not adequate. We will see as we go on that the laws of physics, our formulation or what we are deducing from nature is not consistent with the purely once differentiable functions of time.
Sir, is it wrong to say it is thrice differentiable?
If
I just assume it.
You are welcome to assume anything you want, but there may be systems in nature which you want to model which will fail that assumption. So, and not just fail, but the systems that we usually treat in classical mechanics need not satisfy that condition, that they be thrice differentiable. It is not needed at all. But that doesn't mean in many examples it may be thrice differentiable. Yeah, so it may happen, come for free.
Sir, but even in nature, this law isn't apparent, right? Because twice differentiability of trajectory basically implies continuous acceleration, but that is not always true.
Yeah, we are not saying it is always true. We are. I mean, I don't know what you have in mind. I mean, you have made an assertion. If you give an example or what you have in mind, one can.
Twice differentiability imply continuous acceleration.
No, I mean, twice differentiable. I did not say twice continuously differentiable. Okay, you can say twice continuously differentiable. Twice differentiable simply means the acceleration exists. And I'm happy to add continuity. So, okay, so let us say continuous acceleration. Fine. Yeah. My point is that you can observe particles like you observe Jupiter's motion. How do you do it? You sit up at night, you keep a telescope. If you're not so rich, you have your naked eye, you watch it. You have a paper, tracing paper, you put the points at which you see the Jupiter. Yeah, you do it throughout the night, and then you do it for 10 years. All right, you get some nice curves. And then you look whether this curve is differentiable or twice differentiable, thrice differentiable. That's how you find out. This is not something we can simply postulate. And if you see that the motion of a tennis ball does not satisfy this, then this law doesn't apply there.
And sir, is Brownian motion jagged at every resolution? So if I take a very large resolution, if I look at it very closely, even then it will be jagged path.
Yeah, so no, that's a good question. Brownian motion, we understand the microscopic behavior of Brownian particles better now. The reason, see, Brownian particles, namely pollen grains, roughly speaking, at very short distance scales, travel in straight line paths. I mean, I'm ignoring gravity and all. Yeah, they basically, because gravity is very weak for their motion, they move in straight line paths, which are not just differentiable twice, thrice, as many times as you wish are differentiable. But the point is that after a very short ballistic motion, that is a straight line trajectory, there is a water molecule that comes and hits it. So its direction gets changed very abruptly. And then before you know it, another warp molecule has come and kicked it again in a random direction. And its velocity may also have changed. Yeah, so, and these collisions with motor molecules are very, very, very many, and happening very rapidly. So the question is not whether there is a scale on which the particle motion is twice differentiable. Indeed, there is. It is in fact not even twice. It is just a straight line. Yeah. But that is a useless concept for us, because you will not do any Brownian motion study if you take such a viewpoint, because we are not interested in the motion of Brownian particle between two collisions. That is not very interesting. We are interested in the large scale structure of Brownian motion. What is the probability that a Brownian particle will go some distance if you wait certain amount of time? Such questions cannot be answered if you simply work with straight line paths. You have to account for these collisions. And once you do that, it is no longer fruitful. I emphasize this word fruitful. It is not fruitful to model a Brownian particle as one that has a twice differentiable trajectory on the scales of interest. Is that clear?
Thank you, sir.
Yeah, yeah, sure. Any other questions? See, the things I'm saying are far from obvious, and are the distillation of several hundred years of study of nature and thought. And I am only doing what I can at this stage. So please feel free to ask questions, and I may not be able to answer everything, but I will try. But these things require some thought. I certainly encourage you to please, at the very least, you should go back and read these notes. That is the very minimum you should do, because I will go through things a bit fast here. Okay, so having said that we are now studying phenomena where particle trajectories are twice differential functions of time, let us go further. Now we would like to come to what are called Newton's laws. So Isaac Newton formulated three laws of classical mechanics in his Principia. In 1687 it was published. So let's see. So let us discuss Newton's first law. I mean, many of you have certainly come across it. However, I request your patience, because Newton's first law is a very deep statement about the character of physical law, and it requires some understanding. Let us try our hand at it. So Newton's first law, also called the law of inertia, says that, okay, this is the first statement, all right? This is a translation from Latin. Every body continues in its state of rest or uniform motion in a straight line unless it is compelled to change that state by a force impressed upon it. Okay, so let me say that again. Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by a force impressed upon it. So the language is somewhat older. Some of these words we will have to redefine and use in a different way, but I hope you get the idea. Let me state this in a mathematical way. In other words, the momentum P equal to mass times velocity, which is also the mass times the acceleration, mass times r dot of a particle. So momentum is mass times velocity, and velocity is r dot. Okay, so those things we are already familiar with. What we are saying is that if the particle moves in a straight line, it means the velocity, okay, wait a minute. Let me finish reading the sentence and then make my comments. In other words, the momentum P equal to mr dot of a particle that is free. Okay, the word free is used to encode this condition. That is, unless it is compelled to change by a force impressed. So if there is no force, we call such a particle free. So a free particle is one that is isolated or far from physical interactions. Okay? You can say it is far away from Earth and in interstellar space or something like that. Yeah. So for such a particle, a free particle that is not subject to other physical influences, well, the statement is that mass times the velocity of that particle does not change with time. Okay? In which case the velocity would be a constant and the motion would be in a straight line. So this is easy to see. We notice that if r dot does not change with time, namely r double dot is 0, then the trajectory, which we get by simply integrating this equation, r dot equal to constant, would be r of t equal to some initial location r of 0 plus r dot times t. Okay, so you see that this formula is obtained by integrating the equation r dot equal to constant, and that constant is simply r dot of 0. Yeah. Once to obtain the trajectory of the particle, we see that this is the equation for a straight line. A straight line that is moreover uniformly traversed because the speed is constant. And doesn't change direction either. Velocity doesn't change direction. Okay, so this requires many comments. We have not yet really understood the first law, so let me proceed a bit. Any question about what I said so far, at least? Okay, so a remark about free particles, perhaps. So in general, it is found that macroscopic interactions, by macroscopic interactions, I mean, say, gravitational interactions, the force of the Earth on other objects, or the force of the sun on other objects, other masses, decrease with distance. I mean, this is also true about electric interactions. They also decrease with distance. So also magnetic interactions. So it is possible to isolate a particle by taking it far from other bodies. So since we talk about bodies that are free, I have to say how one can create a free particle. You simply take it far away from other things. You may ask how far away? Well, to the desired accuracy you wish. If you want some accuracy, you take it that far. So there are details there, of course, but in principle, this is possible to do. But there is a more serious issue here. It is that we have been somewhat, not just somewhat, rather imprecise in our statement of Newton's first law. Okay, so we have to fix it. It turns out that Newton's first law generally holds only in certain frames of reference. All right. Okay, so this is a big problem. To specify the components of the position and velocity vectors, right? After all, I used them in writing this formula. To specify the components of the position and velocity vectors, we need a frame of reference. Okay, we need an origin, we need concept of time, and we need coordinate axis. So in our previous statement, which was very nice and pithy, short statement, no mention of the frame of reference was made. Yeah, so the question would automatically arise, in which reference frame is this law valid? I mean, is it valid in all reference frames? What sort of a law is it? Okay, so is my question clear to you?
Yes, sir.
Yeah.
Yeah. So when we say in a cavalier fashion, in a colloquial way, that Newton's first law says that in the absence of forces, every body moves in a straight line uniformly. We are omitting certain qualifying statements as to who is observing this particle, yeah, or from which frame is it being observed. That needs to be said. Okay, and that therein lies the crux of the matter. Let us see what the answer to those questions are. Okay, so let me first begin say some examples or some cautionary remarks. First of all, it is found that a particle that is not subject to any forces, that is a free particle, an isolated particle. Yeah. So I've isolated my particle. Sadly, an isolated particle could fail to follow a constant velocity trajectory. Okay, in certain reference frames. So sadly, a free particle need not move in a straight line, need not even maintain a constant speed. Okay, so there is something problematic in this law as stated. What do I mean? Let me be more detailed. So I'm going to give examples of frames where this fails. Okay, so, but let me introduce some terminology here. A frame of reference, by a frame of reference, I mean a choice of origin, and let us be specific, a set of orthogonal coordinate directions. Yeah. And one must say what is happening to that frame. So those is all part of the specification. Yeah. So a frame in which Newton's first law holds is said to be an inertial frame. Okay, so this is just a definition or a introduction of a term. We say that a frame in which Newton's first law holds is called an inertial frame. In other words, yeah. Now, but let me first give an example. So to a reasonable approximation, if when I say reasonable approximation, I mean if one ignores some effects of the rotation of the Earth, yeah, a frame that is fixed in a tennis court, or for that matter, a frame that is fixed in my office, yeah, with the axis along the walls, the edges of the walls, yeah. That frame that is fixed in my office or in a tennis court is an inertial frame for the motion of tennis balls, rackets, and so on. Okay, so so what does that mean? It means that if the tennis ball is not subject to any force, that is, you somehow turn off gravity, you turn off air friction and such things. So in particular, if the effects of gravity and friction are ignored, or somehow you cancel them out, yeah, then tennis balls in this frame would always move uniformly in straight lines. One moment. Yeah, so Shyam Patakar is asking a question concerning this. Is it not possible practically to attach a frame of reference anywhere and everywhere? So Newton's first law should hold everywhere, shouldn't it? Yeah, this is a very legitimate question. I'm going to answer this question. So just hold on. I hope just address these questions. Yeah, so let me just repeat what I said. I'm claiming that a frame fixed to the Earth is, to reasonable approximation, an inertial frame. And by that, what it means is that particles that are not subject to any other forces, would move in straight lines at uniform speed. Of course, this has to be checked. You have to check whether it is true.
Why would they move uniformly?
No,
in straight lines?
This is the experimental observation.
Define force. I thought that okay. So I thought the way you see if a force is acting upon a particle is if it's accelerating. So how do you define a force separate from its motion? Like,
no, see, we have not defined a force so far. We have simply introduced the idea of isolating an object. So let me, very appropriate questions from both Ankon and Anhad. Look, this is an idealization. You are supposed to take your particle to a place where it is not subject to any external influences. Okay, I'm avoiding using the name force because that may have some other connotation in your mind. Yeah, I take it far away from other things. Okay, this is a practically doable.
Other masses.
Other masses, yes, indeed, other masses, indeed, other masses. Yeah, definitely, other masses would be a good idea. Yeah, you want to also take it away from other electric fields and magnetic fields if the particle was charged. Yeah, but let us not worry about such matters. So anyway, you somehow arrange your particle to be far away from other influences, and then somehow observe its motion. The claim is that such a particle if the frame is inertial, would move in a straight line. Let me. We are halfway through this process. So Anhad, yeah, I have not defined any force. I'm simply telling you how to isolate a particle, and I'm claiming that I've not made my claim fully. It's coming. So just a moment. But Anhad, do you want to ask anything right now, or Ankan? Okay, let me go ahead then. Just a moment. I think an example will help to clarify these matters. However, it is found that Newton's first law for tennis balls, when I say Newton's first law for tennis balls, is the assertion that they will always move in straight lines at uniform speed in the absence of other forces, in the absence of other influences. Okay, so somehow you have to turn off gravity. Okay, that is your problem. There are ways to do that. Okay, so somehow, I mean, if you really want to do it in a tennis court, it's a bit difficult. You would need to somehow cancel out the effects of gravity. Maybe you make the tennis ball charged and you put an opposing electric field to cancel the gravity or something. Yeah, you can imagine doing such things. Or you simply transport your tennis court very far away from the earth. Yeah, then the effect of gravity may be minimal or reduced to the desired accuracy. And then you see, does your tennis ball go in a straight line? Always. Yeah. So, but there's a problem. What is it problem? It is found that Newton's first law for tennis balls fails to hold in a frame that is attached to a swinging pendulum or to a rotating merry-go-round beside the tennis court. So let me say a little bit more about this. So such frames, like the frame of a swinging pendulum. When I say a frame of a swinging pendulum, I mean I have this fixed frame, my room. Within that room, I had that fixed frame. Now I consider another frame that is moving relative to that, okay? Moving in the manner I am showing with my hands. And I observe the particle from that moving frame. I also observe it from the fixed frame. Yeah. Now, if the original frame was inertial, then one would find that the particle moves in a straight line. But then from the viewpoint of this person who is sitting on the swing and watching the ball, for the person sitting on the swing, the ball is not going to move in a straight line. The ball is going to go do some funny motion. Imagine watching a ball moving in a straight line, but if you are sitting in a rotating merry-go-round, you would see a much more complicated motion. Certainly not straight line motion. Not even at constant velocity. Yeah, because at some time your merry-go-round may be approaching the ball. At other times your merry-go-round may be going away from the ball. So at those two times, the velocity of the ball are going to be different. Nevertheless, somebody else who is in this so-called inertial frame would say, no, the ball is moving uniformly. So is this distinction clear to you? That it is possible to go to what would be called an accelerated or non-inertial frame, such as that of a rotating merry-go-round or of a swinging pendulum, in which an otherwise free particle would look to traverse a non-straight line trajectory at non-uniform speed. Okay. So we are coming to the heart of the matter here. Let me give one more example, which I hope will address the issue raised by Shyam Patankar as well as the others, Anhad and Ankan. So for instance, let us go to this faraway place, this spaceship where there are no external influences. And I have a particle in that spaceship. And you have a frame fixed in that spaceship. So that particle will be at rest, for example, okay, just sitting on the floor of the spaceship. Now let us do something. Now we introduce another frame in that spaceship, namely a frame that is attached to a bee that is flying irregularly in that faraway spaceship. Okay, so I situate myself on a bee that is zooming around this spaceship, and I have a frame that is fixed to that bee. According to the bee, the particle is not even at rest and is moving irregularly, because when the B comes near the particle, the particle is coming towards the B. Yeah. So
can you please again repeat this whole point?
Yeah, I will repeat it because this is a subtle issue. I go to a faraway spaceship. So far away means away from all other physical interactions, like gravity is minimized as much as we can. Now, such a frame is called inertial. Okay, a frame fixed in an isolated spaceship. It's inertial because particle at rest in that spaceship will not move. Newton's first law will hold. Okay? It will not. Or if you set out a particle to move in that spaceship, you push it initially, it will continue moving at the same velocity. Okay, so this is what is observed. This is what I want to assert. We are deducing from nature that there is a frame called an inertial frame where free particles move in straight lines at constant speed. Okay, so this is our observation. However, not all frames are inertial. So we are just constructing a non-inertial frame. What would a non-inertial frame be? It would be one in which a free particle appears to follow a trajectory which is not a straight line or not at constant speed. Okay. Let me give an example of such a frame. It would be a frame, this frame. Okay, so this is my spaceship. Particle is at rest. So the particle is my nose, tip of my nose. It is at rest, doesn't move. But now the frame is attached to a bee which is moving around. Okay, so the bee is zooming around, thankfully not stinging me, but coming and going. Yeah. According to a person who is sitting in this frame, they will say that the tip of my nose is not at rest. Okay. Not only is it not at rest, the tip of my nose is moving non-uniformly, because at sometimes the person who is situated on this frame will think that my nose has come close to it, close to the person, and at other times it has gone farther away, and it is also in the different locations, distances, and the bee is moving non-uniformly. So, so a particle that was at rest relative to that fixed frame in the spaceship does not appear to travel in straight lines as viewed by this other observer who is attached to the bee.
So to sum up, you are saying that in non-inertial frames, Newton's first law will not hold.
Exactly. Yeah. In a non-inertial frame, Newton's first law need not hold. Indeed. So let me come back. Very good. Yes, you did say it correctly. Okay. Let me not talk about bees too much. Yeah. So let me give you one more example. Similarly, let's come back. Yeah, B may be somewhat difficult. Oh, I'm sorry. Have I lost my connection? One moment. Yeah, so I hope you're now able to see my screen. So if you don't like bees or merry-go-rounds, we can take a top. I mean, you're familiar with a Pambaram in Tamil, or I think it's called Lattu. Yeah, so a spinning top. Yeah, suppose you attach a frame to a spinning top, so that frame will keep rotating. And then you observe a free particle that is at rest from that rotating spinning top. According to the person who is sitting on the top, that free particle, which otherwise is at rest, according to me, would be going round and round. Certainly not in a straight line. If at all, at the very least, they would say it's going around in a circle. So a circle is not a straight line. So from a frame fixed to a rotating top, a free particle does not execute rectilinear motion, uniform rectilinear motion. So it is clear that there are frames in which Newton's first law holds, I mean, as stated before, and there are frames in which it doesn't hold. So now we need to restate Newton's first law in a better way. So let me try to do that.
Earth is moving in an ellipse, right?
Yeah, so the Earth is moving through the solar system. Indeed, yes.
How is it a approximate reference frame?
How is it? Could you say that again, Anhad?
Why does you said that Newton's first law holds approximately on Earth, right?
It does. Yeah. See, it doesn't exactly hold. You are quite right. The Earth is not an inertial frame. A frame fixed to the Earth is not inertial. But see, it's a question of what accuracy do you want? I mean, you make an experimental measurement of the trajectory of a particle, and the question is it a straight line, one part in 100 or one part in 200 or one part in a million? You have to decide your tolerance. What are you going to call a straight line? I mean, a trajectory that is straight to what accuracy? Now, if you are satisfied with a certain level of accuracy, the fact that the Earth is rotating may not matter. The effect of that may be small and may be ignorable. So, and that is indeed the case for many purposes. The Earth is in fact can be treated as an inertial frame. A fixed frame fixed on the Earth can be treated as inertial. I will say, let me make a few remarks about that. Yeah, so just hold on. So let me come back. And to summarize, Newton's first law, yeah, I'm now restating Newton's first law. Okay, after all this discussion, Newton's first law is the assertion that there is a frame of reference called an inertial frame in which all isolated bodies, by isolated I mean far from physical interactions, move at constant velocity. Okay, so I have completely restated Newton's first law. What we said initially is not to be taken literally. This is a restatement now. Let me do this again. To summarize, so Newton's first law is the statement of the existence of certain frames. That is what it is. Newton's first law is the assertion that there is a frame of reference called an inertial frame in which any isolated body, not just any, all isolated bodies, which are far from physical interactions, move at constant velocity. Okay, so that is what Newton's first law says, that it is possible to find a frame in which an isolated body will always look to be moving uniformly rectilinearly. Okay. You may ask the question, is that inertial frame unique? Well, answer is, as we will see shortly, from a principle enunciated by Galileo, an inertial frame is not unique. So there are many inertial frames. Yeah, if you find one, you can find others by a procedure Galileo has taught us. Okay, so I have just stated Newton's first law. So please come back with your questions or request for clarification. Anything?
So Earth is approximately a good reference frame because it's like moving, like its trajectory, the radius is really huge. So in short time intervals, it's as if it's moving in a straight line.
No, see, we are not. Okay, there are several issues here. Let me, you're mentioning that the Earth is moving around the sun in an ellipse. That is true. And yes, ellipse can be approximated by a straight line for short times. That is all fine. But that is not quite relevant here. What we are asking is that if you have a particle on the Earth, moving with the Earth, you see the Earth is moving and we have a particle here in which I'm holding in my hand or kept on the table or something. Yeah. We're asking that if we are able to eliminate all forces from that particle, then
how is it moving along with the Earth if we have eliminated all forces?
Okay. Okay, that is why. Okay, your point is well taken. That is why we go to a faraway spaceship. Okay, no, I mean, I take your question, but that's why we go to a faraway spaceship where there is no issue about Earth moving and so on. But no, we can state it in terms of the Earth also. If you, I'll try.
But that we can state in terms of, like, we can always move along with an accelerating body, right?
Yes.
Any accelerating body. So I didn't get that.
Yeah. Okay, so let's do this a bit more carefully. okay, the assertion is that see, the assertion is that free particles, if you have an isolated body that is free from all interactions, then you can find a frame in which it moves at constant velocity. That is the assertion. Now, if you want to apply that to the Earth, you have to be somewhat careful. If you want to, and I need to understand precisely what you are saying. What are we saying? We are saying that if the Earth is isolated, that is the sun's gravity is switched off and Jupiter is also switched off, then the Earth will move in a straight line at constant speed. That's what we are saying. But that's probably not what you are asking. So I need to be more clear about what you're asking. A moment.
Be like, okay, for example, we formulate Newton's laws from Earth, right, which is itself an accelerating frame.
Yeah.
So okay, so what you're saying is, if say even in an accelerating frame, if
no, see, the question is the Earth's acceleration around the sun relevant to the phenomenon you are studying? Namely, the motion of a projectile from here to the next room. Answer is irrelevant. It doesn't matter at all for the most part. There is a part that matters, and that is the rotation of the Earth. It has a small effect. Now, even that is a very minuscule effect. So let me put it this way. You have to do careful experiments. You need to ensure that your projectile see, the principal force here is that of gravity. Okay? So you have to somehow cancel that off. Yeah? So you have to do some clever experiment where you can cancel off that gravity and then observe the projectile. Yeah, and if you find that it moves in a straight line at constant speed, then you will conclude that the frame you are constantly studying is an inertial frame. And that can be done, and doing that one finds that the frame fixed to the Earth is reasonably inertial.
Sir, does that mean that Earth is not actually a inertial frame, but we can take that tolerance for our experiments, and if we want to be, if we want to be like perfect inertial frame, then we should go very far from any celestial bodies like in a spaceship, like that.
Exactly, you are right. You're right. See, there are more sophisticated things we can do, but see, we are not always only interested in free particles, right? We are also interested in particles subject to forces. But suppose you are wanting to study only Newton's first law and stay within that and check it. There are two options for you. One, you go far away from all bodies. And then you check whether your particle moves in a straight line in the frame that you are constructing, and then if so, then you will conclude that that frame is inertial. Okay, so that is one way to do it. Another way to do it is to somehow eliminate the effects of the forces that are anyway present on Earth, and then check whether your particle moves in a straight line. So one can do either of them, and if you find that it is the case, then you will say that the Earth is inertial to the desired accuracy. Let me give you an example where the desired accuracy will tell you that the Earth is non-inertial. So I'm running out of time actually, but okay, let me try.
My question was, suppose there's suppose there's an object, a frame which is different, separate from the Earth. So now from Earth, how will we know if that particular frame is a inertial or non-inertial frame?
You have to do experiments to find out. See, a frame is inertial if free particles move in straight lines with respect to observers in that frame. Okay, that is the statement. So you are asking, is the Earth's frame inertial or not? I have told you a way to check. Let me tell you one more way. Let me tell you one more way. I mean, not just a way to show that. Okay, let me just read what I have here for a moment. Maybe this will help you a little bit. there are indirect ways to check whether a frame is inertial or not, even if one cannot isolate particles. Okay, so I'm getting ahead of myself, but let me just state this. This makes use of Newton's second law, which is also a statement about inertial frames. Okay, it turns out that Newton's first and second law both are statements about inertial frames, but anyway. So let me tell you what it is. Roughly speaking, suppose we assume a frame is inertial. Okay, so somebody tells you Earth is an inertial frame, so we assume, okay, suppose that is the case, let us try and see what happens. We deduce consequences using Newton's second law. Okay, so this is going beyond the first law, but we deduce consequences based on Newton's second law and find that they are experimentally violated. Okay, suppose that happens, then one possible reason for the discrepancy could be that the frame was not inertial to begin with. Okay, so that the hypothesis was wrong. Okay, so there is a concrete realization of this. This is called the Foucault pendulum. So this is a pendulum with a heavy bob and a long string attached to it. I mean, it's really very long. So it's hung from the ceiling of the Pantheon in Paris. Yeah. So this gives a concrete realization of this idea. And one, by studying the Foucault pendulum and applying Newton's second law to it, one concludes that the plane of oscillation of this pendulum should be fixed. Okay, but what is found is that the plane of oscillation of the pendulum actually rotates. And then you will infer that the assumption that Earth was an inertial frame is wrong, and Earth is not really inertial, and the rotation of the Earth is causing this discrepancy. However, this discrepancy is very small also, right? So for many purposes, we can treat a frame fixed on the Earth as inertial. Okay, so Anhad and others, please ask if I am not clear yet.
Can we ever find any frame that is, I mean, absolutely inertial? I mean, for example, Earth is not.
See, this question of absolutely inertial is not physically meaningful, right? We never have infinite accuracy in any measurement. So it's not a meaningful question. You give your tolerance, I answer your question to that tolerance. So if you want accuracy to 1 part in 10, then maybe the Earth is inertial, but maybe it is not if you want accuracy better than that.
Okay.
Sir,
Yeah, so, okay, I mean, this may sound bad, but we'll talk more about this. Yes, please go ahead. Yeah.
Sir, how do we detect whether we are in an inertial frame? Like suppose.
No, we are. You have to tell me a frame. It's not about we are in an inertial frame. You have to select the frame, then you can ask the question: is it inertial or not? Okay, so when you say we are in, let me interpret your question as saying a frame fixed to your body. Okay, so your body is here. I fix a frame, right hand, left hand, and the rest of my body. Okay, so that defines my frame. So I think that's what you mean by we. Let me assume that is the case. Are you okay with that so far, Ryan?
Yes, that is what I meant.
Okay,
yes.
so now I am my frame. Now I can ask, is my frame inertial or not? What must I do? I must get friends to do experiments because I am keeping my hands fixed. So somebody has to bring a ball which is not subject to any forces. Yeah, and see whether, and then I have to observe, is that ball, if it starts at rest, will it remain at rest? Or if it starts out moving, will it remain moving in the same direction at the same speed? I must perform those experiments, find the results, and then I can answer the question, is my frame inertial or not? Okay, so with first law, that's all you can do. If you have second law at your disposal, you can do a little bit more. So am I addressing your question? That is, I can answer the question experimentally whether my frame is inertial or not. This is an experimental question.
Yeah, sir, that we assume that my friend's frame is inertial?
That friend is simply sitting next to me. What do you mean by, if that friend is doing some dance around, then that frame is not inertial. I mean, it's not. If mine was inertial, then his would not be inertial. They cannot both be inertial. If that friend is spinning around.
My question is that, like how do we detect whether there is some force behind body or not? Like I don't know, if I just see a body moving, how do I know there's a force behind?
You have to isolate it. You have to take it away from other bodies. At present, this is our own. I mean, I told you there are two ways. How do I know whether there's a force on a body? Well, you don't know fully well. Yeah, you need to check. You have to play around with it. It is based on your belief. Yeah, you believe that this body doesn't feel any force. Okay, somebody can check. Yeah, but no. Let me let me say that better. Yeah, if you want to isolate a particle, simply take it far away from other things. If you want to stay on Earth and you're aware that there is gravity, then you're aware there is a force. You want to get rid of that force, you somehow cancel it off. Yeah, you do your best, and then check whether if it starts at rest, it remains at rest, and if it starts moving in some direction, it remains moving in that direction. If it fails to do so, then you will say that either my frame is not inertial or that body is not free. Now, this is a back and forth game. There is no absolute answer to these questions. You know that your body is free because you have done 5 experiments, they all came out like this, so I believe it is free. That is the nature of our subject. You may do more accurate experiments and find that it doesn't follow straight line trajectory. Then you will say, no, it either is subject to some force, or maybe my frame itself was not inertial. You will not need to examine both of those hypotheses and then see what you can say. So I think the summary of this is that detecting whether a frame is inertial or not is no simple business. Yeah, you need to. It's a back and forth process of experimentation and checking things. So please, any further questions right now? I mean, we can continue this discussion. But to Shyam's question. Is it not possible to simply attach a frame anywhere and everywhere so that Newton's first law should hold everywhere? No. See, the statement is that every free particle must follow a straight line trajectory. All right. So if Shyam is still here, let me give you a very concrete thing. I go to my spaceship. I have a free particle that is simply sitting there. I have another free particle that is moving in a straight line. I also have some observer who is moving randomly through that spaceship. Suppose there's a particle fixed to that randomly moving observer. According to that observer, that particle is always at rest, doesn't move at all relative to that observer. So that observer would have found that there is a particle which he believes is free because everything is isolated and is at rest. So that observer may say, okay, my frame is inertial. But no, wait a minute. Every free particle must move along a straight line. So let that same observer now observe the particle that is at the corner of that spaceship, which is not fixed to his frame. According to that observer, that particle in the corner of the spaceship is going to go randomly moving around because he himself is moving around. So the conclusion that randomly moving observer made initially is false, because it is not true that every free particle moves in a straight line. It's not enough for one free particle to move in a straight line. Every free particle must move in a straight line. So you must do many experiments. You do 5 experiments, you feel you are happy, and then you go forward. You find some discrepancy, you come back. This is the way it works. Is that helpful?
Yes, thank you.
Okay, all right. So maybe this is no. I mean, Newton's first law is by no means a trivial statement. So it is worth thinking about. All right. Any other questions? Yes.
Sir, if Newton's first law, if and only if condition. So it says that momentum is constant if no force is applied. But if I say that a force is applied, but still momentum is constant, in some situation, force is being applied, but the particle is not moving. Does that violate Newton's first law?
No, wait a minute. So Newton's first law states that that if you have been able to isolate a particle, then there must be a frame in which it moves uniformly. Yeah. So what are you saying?
Only ignoring. So we are wholly ignoring the initial statement, right?
What do you mean initial statement? Which statement?
I mean the classical statement and not the reformulation you gave us.
Yeah. Classical statement has to be thrown out. I mean, it is incomplete. We have to give further qualifications. Otherwise, it's not proper.
And sir, if we know from some frame that a force is being applied, but the particle is still not moving from that observer's perception, can we conclude that observer is sitting in a non-inertial frame?
Oh, okay. So wait. I need to think a bit about that. So you're saying that. I mean, the first law doesn't make any assertion about that. It is simply the existence of, but maybe one can deduce something of the sort you are saying. You're saying that you are aware that the particle is not free, but still not moving according to your perception. Okay. Okay. I'll try to think about that. Not very sure about whether we can conclude that the frame must be non-inertial. Okay. Yeah, perhaps you are right that if had it been inertial.
Can I ask one more question?
Okay.
Sir, when we say force, we oftentimes say a force, but we never say a velocity or a acceleration. What is the I have oftentimes seen that it is referred to as the force of the force of somebody, force of the cart or force of the horse. There's different forces of somebody. It's a personal thing sometimes, and sometimes it's called a force. So how is force different from any other quantity like acceleration? Is it not simply the differentiation of momentum?
No. Force is not differentiation of momentum. Definitely not. No. Acceleration is, I defined the concept of a position of a particle, and then we talked about the trajectory of a particle. From the trajectory of a particle, which is a curve, it's possible through purely calculus procedures, namely differentiation, to find its velocity and at the next step get its acceleration. So this is a purely geometric and calculus approach. You're able to define concept of acceleration. Force doesn't have any such description. Force is a completely different concept. I have not talked about it in any serious way yet. That will come when we discuss second law. The force is. I will describe next time how we may want to, maybe how we can deduce the forces using a certain physical law framework, such as Newton's second law. Okay? The concept of a force doesn't a priori have a meaning, a precise meaning without such a framework. You may have some intuitive idea that a force is something that you apply when you push a ball, or when the earth pulls things towards it, or when other bodies pull the earth towards it. Yeah. So the force is can be intuitively regarded in that way, but it is not something directly defined in terms of the trajectory of a particle. Certainly not. The force is not the derivative of momentum. I mean, that is some second law. We have not come to it. We'll talk about that.
So we can. So I would please like to know, whenever time comes, like how do we say that a force is applied by somebody instead of somebody else? How do we say a force is personal? It's a possession. So I would like to know about that.
Okay. No, I mean, if I press this table, I think it is our common experience that I have eaten breakfast and I have some energy and I am pushing it. You are not inclined to say that the. So what is the other option you are offering?
No personals. Nothing is personal everything is just like, if there is a force, I don't know whose force is it. I don't want to take, like, I want to think of, there is no component forces. There is just an aggregate force. There are no components. It's just one vector, and it cannot be divided into two components. Like there is, so if I think about pendulum, there is only one force. We can split it into tensile force or a gravitation force. Just one force, which I will call ping-pong force.
No, I didn't mean to say that this is something personal to me, that I am just giving an example. When I press the table, I am exerting a force on the table. This is our understanding. But yeah, you're right. If you are considering a pendulum that's moving in the Earth's gravity, indeed, yeah, it's subject to a couple of forces, at least the important ones, the tension in the string and downward gravity. These are present. And it is very useful to resolve the net force into these constituents. I would certainly want to have the freedom to do that. Yeah.
So, for example, we assume the tensile force to be force of the wire and a gravitation force to be force of the earth.
Okay.
So, yeah. So how do we determine? My question is, how do we determine whether this force belongs to this person or not?
We switch off one of them.
Yeah.
No, you switch off one of them. If you believe that the tensile force is due to the earth, then you cut the string and see whether that force is still there. Yeah, I mean the tensile force is.
So we make something first. Yeah.
See, you do it by elimination.
So So if you want to check whether a force belongs to something, I make it stop existing and I check what is subtracted from the total force.
Yeah, that's a good way. Yeah, that's a good way. You somehow switch off the earth and see whether the tensile force is still there or not. Yeah. So it's possible to do such things. Yeah, by being clever, you can switch off the effects of the earth. Simply put some charge on the bob and then repel it with something. You may be able to cancel out gravity, at least to some approximation. Yeah. Yeah, so we try to isolate certain effects from others and thereby attribute causes. Yes, that is how we proceed.
Thank you very much, sir.
Yeah, so we'll talk more about forces. I mean, the force is a completely different concept than acceleration. Yeah, and Zeroth says that force is a physical thing, not an abstract construction. Well, if you interpret the statement in the way I said, yes, sure. It is, yeah, we will try to say what we mean by force as a mathematical concept, but yeah, it is certainly not the acceleration. I mean, there is a law that relates the two. That's a different matter. Okay, any other questions? Okay, I know I have gone beyond the time, but I hope to have at least begun addressing some of your very pertinent questions. If not, let me end this meeting here and wish you all a good afternoon. We will meet again next Tuesday. Thank you.